In this video, I will talk about regression with indicator variables in Stata. Before you watch this video, please make sure that you have watched my other video called Regression with Indicator Variables. So I have opened up the program here and I highlighted it and executed it, and here is the output. So in this presentation, we will talk about single indicator variables, then interaction terms with another indicator variables, several related indicator variables, interaction terms with non-indicator variable, and F-test and Chow test for differences across groups. So go ahead and download wage1.dta data file and put it in the directory where you can read it and execute the program. So the first thing that we will do here is to look at the single indicator variable in the regression. So we would be using this data file, wage1, and we would be running a regression of wage, and then we would be summarizing wage. So at this point, we would have no independent variables. And this is how the output looks like. So if we just have a wage regressed on a constant, then a 5.90 is basically the average wage for people in the sample. And if you do summarize wage and you look at the mean, that would be actually exactly the same number, 5.90. Okay, the next analysis that we can do is we can regress wage on female, and these are going to be the outputs here. So if we regress wage on female, the coefficient on female would be minus 2.51. So the way we interpret this coefficient is that females are getting $2.51 lower wages than males. This constant here of 7.10 is the average wage for males, because for them, female is equal to 0. If you would like to calculate the average wage for females, these two coefficients would need to be summed up. So this 7.10 minus 2.51 would be the intercept or the average wage for females. So if we look at the summary statistics for groups of males and females, we can bisort female and then summarize wage. So this means summarize wage for the groups of male and female. And this is what we see here. For females, wage, the average for females equals 0. So this is actually the group of males. The average wage is $7.10. And for the group of females, the average wage is $4.59. And so these numbers are exactly the same numbers that you will see here as the intercepts in the regression. So here is this $7.10. That's the intercept for males. The intercept for females is this number plus this number, which would be exactly $4.59, which would be the intercept for females. If we want to do a more formal t-test to compare the average wage for females and males, here are the statistics. You will see these means are here again. This is the number of observations that are male, and this is the number of observations that are female. This is the total number of observations. So this is again the average wage for the whole group. This is the average wage for females, the average wage for males. And so if you look at the difference between the two is actually 2.51. So that's by how much the wage for males is higher than females. And if you look at the t-statistic here and the p-value, we're concluding that actually these the wage for male and female are significantly different from each other. If you actually look back at the regression analysis, you would see the t-statistic here is the same as the t-statistic here, and the mean is exactly the same. This is the value of the coefficient, and the p-value would be the same as well. So again, generating a dummy variable of female and including it in regression is the same as comparing the average wage for two different groups. So here we can do the graph of wage on female, and we would use graph two-way, scatter wage on female, and then we will do a linear fit model of wage on female because I want to see the regression line for this regression. So if you execute this line here, this is the graph that you will actually see. Okay, so now we have a graph here of female against wage. Notice that all the points are here on just two different points. So we only have the values here for males and the values here for females. So this is why this graph looks strange like that. And the slope of this line is that minus 2.51. That's the coefficient on female. And the other thing that's noticeable here is that this intercept here would be 7.10, and this intercept, well, this is the intercept for women, which would be 4.59. So that's how this one looks like. Okay, so let's continue on. So the next thing we're going to do here is generate an indicator variable for male. And let me show you this part of the code. So male would be equal to 1 minus female, and we would be comparing a regression of wage on female and regression of wage on male. So one thing that we will find here is that the coefficient on female is minus 2.51. The coefficient on male is plus 2.51. And if you look at the significance level, the standard error, t-statistic, and the p-value, they would actually be exactly the same. So we would say we would have same magnitude but opposite sign of these coefficients. And again, here we would have the intercept would be the average value of wage for males. And if you do this plus this coefficient, that would actually be exactly this coefficient, 4.59. And this will be the average wage for females in a regression that male is the independent variable. If you want to find the intercept for males, you have to sum up this coefficient plus this coefficient, which will actually result exactly in that value, 7.10 as the intercept for males. So you can obtain these things like that, one regression from the other, and it's preference which one you would like to estimate. So now if you want to estimate a regression with both female and male, they cannot be estimated because of perfect collinearity. One of them has to be dropped. And so if you attempt to put both of these variables in here by doing regression of wage on female and male, you will see that Stata actually automatically drops one of them. So you would not be able to estimate. One way to go around this is to estimate a regression of wage on female and male, comma, no constant. So if you actually see there is like a no constant in this. So because there's no constant, this is not a very typical approach that we use. But actually, if you look at the coefficients, this is the average wage for females. That's the average wage for males. But again, this approach is not commonly used. Now, let's consider interaction terms with another indicator variable. So for this, we would generate another indicator variable called single, which would be 1 minus married. And so now we want to form categories which are female times single, male times single, female times married, and male times married. So we would basically multiply these individual indicator variables to get an interaction term between them. And if we list them, the indicator variables in interaction variables, we can do list. We can list the original variables and then the interaction terms. This is what we're going to get. So here we have female equals 0, male equals 1. So that's a male, and this person is married. So then the next variable here is, let's see, female and single and male and single, and then male and married and female married and male that married. And so this one is a 1. So in case we have a single, a male who is married, we would only have the dummy variable for male married equals to 1, and all the other 3 dummy variables would be equal to 0, and so forth. So here, if we have a male that is single, only the male times single indicator variable would be 1, and the other 3 interaction terms would be equal to 0. So this is now how the data would look like. And so next, let's go ahead and estimate a regression where if we try to actually put all of the 4 categories in here, all the interaction terms, theta would drop 1 because we have perfect collinearity. So here in this case, the male single variable was dropped, and these were the estimated coefficients. So now let's go ahead and we can pick which one to be the reference category. And in order for this to be a reference category, this variable will not be included in the regression. So when we do a regression of wage on, you notice that the male single is not included in here. So that's why that's the omitted category, and this is going to serve as a reference. So now, if we would like to know what is the marginal effect of being female and single on wage, we can look up this coefficient here. So we can say that single females are getting 56 cents lower than single male, because that was the reference category that is not included. But notice that this coefficient is not significant. So if we want to calculate the marginal effect for female and married, this one is the female and married, so that would be 60 cents lower than single males, the reference category. So that's how we're going to say this, but again, this coefficient is also not significantly different from 0. So we can also estimate a regression using alternative categories, and those categories would be female married and female times married. So this is what we are going to do here. We would generate that variable female times married, so by multiplying female times married, and we would have a regression where we have an independent variable that is indicator, the other one, and then the interaction term between them. So this one is a little bit differently specified than the regression that we have here. We still have 3 dummy variables, but these are composite variables of all of the individual variables, whereas here they're the standalone individual indicator variables and then the interaction term between them. So let's look at how this regression looks like. And so here we have, these are the coefficients in the regression that we estimated. So if we want to know what is the marginal effect for female and single on wage, so if it's female, we would need to collect this coefficient, and if it's single, that variable would be equal to 0, and that variable would be equal to 0 for single people. So it's basically just this coefficient, and it's minus 0.56. And so this coefficient also is not significantly different from 0. So this is the marginal effect for female and single on wage. And if you go back, you will see that this was exactly the same effect that we estimated before. Now, if we want to calculate what is the marginal effect of being female and married on wage, if it's both female and married, we need to collect the coefficients on this variable. Married would be equal to 1, and therefore their interaction term would be equal to 1. So we would need to sum up all of these three coefficients. And when we do that, if we sum up the coefficient on female plus the coefficient on married plus the coefficient on the interaction term, we would get 60 cents. So basically 60 cents lower. That would be the marginal effect. Okay, so next let's talk about several related indicator variables. So regression that has several related independent variables that are indicator variables would need to drop one as reference category. So here we would be looking at the regions that each of the workers are located. So we have north, central, south, west, and east. And we're generating the east region by doing 1 minus the other regions. So here is what we have in the data set. So here we have the proportion of people that are in each of these regions, basically. Okay, so let's summarize the average wage by region. And we can summarize wage if the first region is equal to 1, or if south is equal to 1, or if west is equal to 1, or if east is equal to 1. And these are the summary statistics. So we have that the average wage of people that are located in the north central region is 5.71. For people living in the south, their average wage is 5.38. And for people living in the east is 6.36. So notice one thing is that the wage in the west is the highest amongst the four wages, and then it's followed by the wages in the east, by the south, I'm sorry, by the north central region, and then the south are the lowest wages. So first, let's estimate a regression with east as the reference category. So you see like how east is not included here. The other three independent variables are included, but not east. And then we can estimate the regression with west as the reference category. And now west would be the excluded variable. So let's see what we see here. So these are the two regressions that we just ran. So if east is the reference category, we would be saying here that say if you live in the south, the wages are 98 cents lower than wages in the east, because wages in the east is the reference category that we have. And this coefficient is significantly different from 0, but the other coefficients are not significantly different from 0. Therefore, wages in North Central and the West regions are not significantly different than wages in the East. So if we actually pick up now West as the reference category, so West is the one that's not included, we would have that in comparison to the West, North Central region would have 90 cents lower wages, and then South would have $1.23 lower wages in comparison to the West. So if you look at these constants, this constant actually is exactly the average wage for the reference category. So this is the average wage for the East region, and this is the average wage for the West region. And notice that this coefficient and this coefficient are the same but opposite in magnitude and significance, but opposite in sign, because how the wages in the West relate to the East are exactly the opposite of how the East relates to the West, which is the reference category. And the others you can obtain by just by just doing a transformation. So for example, if South is 98 cents lower than the East, actually then the South is $1.23 lower than the West. Okay. So these are again direct comparison of the average wages in these 4 regions. So if you look at, again, if you look at these numbers, you will see these numbers, this one and this one, exactly in the table there. And what we are comparing is one number to the other. So we've had more significance in the second regression. Why? Because if we have the West as the reference category, this one was the highest value, so that everything is significantly different from it. Okay, so next we will consider regression with East as the reference category and West as the reference category, but this time we would also include an independent variable, education. So if we have education as independent variable here, we would not have exactly, the average wages being the intercept and so forth, but we would see exactly the same kind of trends. So here we would have that for each additional year of education, we have 53 more cents in salary. So this again is independent of the regions. And then we have here, we could compare with the East regions and decide which um, wages in which regions are significantly higher or lower. This is how we would interpret these coefficients here. And we see that actually none of them are significantly different from 0. And here, again, we would see this, but now we have significant difference from 0 here for this coefficient and here, because the p-values are less than 0.05. So we would say here that wages in the north central region are $1.01 lower than the wages in the west region, which is the reference category, and wages in the south are 94 cents lower than wages in the west region. So that's how we were going to interpret this. Next, we will do interaction terms with a non-indicator variable. And so the first analysis that we will do here is regression of wage on education. So if we just have wage on education, that would implicitly assume the same intercept and slope for females and males. So if we do regression of wage on education, and then we do graph two-way, and we do a scatter plot of wage against education, and then we do a linear fit of wage against education, this is what we're going to find actually as the graph. So the graph would be equal, it'd be just one graph for both males and females, and we have a positive slope. This positive slope is equal to 0.54, and the intercept is minus 0.9. This is basically when this line is going to hit the 0 here. And so this is how the graph looks when females and males are combined into one regression. Okay, so now instead of just estimating one regression for males and females, what we can do is actually estimate a regression of wage on education and female. And so here this model would have the same slope on education, but it would have different intercepts for males and females because we have female here included separately in the category. So we can predict, we're going to call it a wage hat, comma XB. So we're actually getting the fitted values or the predicted values. And the reason we're getting this is because we want to plot with graph two-way wage against education. And then we would actually be picking up linear fit of wage against education if female equals 1, and wage against education if female is equal to 0. And so here's how this regression is going to look like, this graph. So now, if we have a regression here that now has female in it. So if we look at the regression results, here we see that the slope is 0.50. So basically, female. So if your education is higher by a year, wages would be higher by 50 cents. That's a significant coefficient. Now, if you're female, you would be getting $2.20, 27 cents lower wages than males. And that coefficient is significantly different from 0. So the constant here would be 0.62. 0.62. So now this graph here would represent the two lines for the regression lines for males and females. So the males is higher, the females is lower. And the difference between them is exactly this 2.27. That's the coefficient here on females. So here we have same slope, which is 0.5 for males and females. You see how these lines are parallel, but we have different intercepts. So the intercept for males would be 0.62 right here, and the intercept for females would be actually this number plus this number, and that's going to be a negative number right here. So again, we have parallel lines here. Okay, so moving on. Now, what if we want to have a regression of wage on education and male instead of female? So if we estimate this other equation, notice what will happen. So here we have the same coefficient on education, but the coefficient on female is now the opposite in sign. So here we said that females are getting $2.27 lower wages than males. Here we would say that males are getting $2.27 higher wages than females. And so notice this constant here, minus 1.65. This is actually where it's going. This is the intercept for females this time. If you want to get the intercept for males, is this number here, plus this would be a 1 if it's a male, so we would have to sum up this coefficient. The summation of these coefficient actually is going to be exactly that same number. So here, this is actually the intercept from males because then female would be equal to 0. If female is equal to 1, the intercept for female would be the summation of these two numbers, and that's that number. So this is actually like a circular thing that you can get one of the numbers from the other numbers. So notice again that the magnitude is the same here. The only thing that's opposite is the sign. Here we have minus, here we have plus. The standard errors are the same. The significance is the same. So we actually have the same significance and magnitude, but opposite sign. So now we can actually run a regression of wage on education if female equals 1. So this will be a regression of only the females. Notice how we have fewer observations. And we can do regression of wage on education if female equals to 0. So this is basically the number of males in the sample. And so if we actually look at these different coefficients and intercept, they would be actually the these will be the intercepts for female, and here will be the intercepts for male, and then the slope coefficient for female and the slope coefficient for male. So next thing is let's graph two-way, and then we will use the scatter for wage against education, and we will do this for females equals 1 and for males equals 0. And so we would basically be plotting these two separate regression lines for males and females. That's going to be the last graph here. And that's what we're going to find here. So if we have a graph like that, one thing that we will find is that they have different slopes. So these different slopes are actually the slope here, 0.53 would be the slope for males, and 0.45 would be the slope for females. So the regression line for males is this one. It's a little bit steeper than for females, which is 0.45, which is a little bit flatter. And they would also have different intercepts. So for females, it would be minus 0.99. For males, would be 0.20. So this is where that would hit the 0 as well. So again, different slopes and different intercepts in here. So if we remember actually these values, this is one way in which we can have different intercepts, different slopes for females and males. Okay, so now let's think about how we can do it using regressions. And so how we can do it if we generate a variable called female times education. We just multiply these two. And now we run a regression of wage on education, female, and female times education. So what this would accomplish is basically now we can have different intercepts and different slopes for males and females. And so here we would get these regression results here. Now, if you notice this coefficient here, that's the slope for education, but this is exactly the slope for education for males in the previous regression. If we want to get the slope of education for females, we need to do this one plus this one, because now females will be equal to 1. So this plus this would be equal to 0.45 that we saw before. Now, this intercept here is the intercept for males. If we want to find the intercept for females, that female would be equal to 1. So we would do this plus that, and that would be the minus $1 that we got before. So again, we have exactly the same results, whether or not we use a regression where we have female here included independently, that allows for different intercepts, or the interaction between female and education that allows for different slopes. Or the other approach was to estimate wage on education separately for males and females. So here I am basically showing you how to calculate the intercepts and the slopes for males and females. Here the intercept for males is just the coefficient on the constant, and so we're picking up this coefficient. The intercept for female is the coefficient on the constant plus the coefficient on females. So this is the minus 1. And the marginal effect of education on wage for males is the coefficient on education. So this is this coefficient. And the marginal effect of education on wage for females is these two coefficients here, the coefficient on education and the interaction of female and education, and that would be 0.45. So these are the same coefficient as running the two separate regressions for females and males that I showed you. So whether you do this way, right here, or this way by just having one regression is equivalent to each other. Okay, so now finally we want to test for significant differences across groups. In order to do that, we would be running an F-test for differences across groups. And so let's just read in the data set again, and we would be generating interaction terms of female times education, female times experience, female times tenure, just multiplying these variables. And here we want to know basically if these interactions, if interaction terms are going to be jointly significantly different from 0. So here we have the unrestricted model where we have wage regressed on education, experience, tenure, and then we have female, and then the interaction of female with all of the independent variables. So this is the unrestricted model. So here we have regression of wage on the 3 independent variables. Female is included separately because that's going to generate different intercepts for males and females. And then we have the interacted variables between female and the independent variables. So this is our unrestricted model. Our restricted model, if we want to know if they're our restricted model would be here, where we have wage equals education, where it would be a regression of wage on education, experience, and tenure. Notice that we actually restricted all of these coefficients to be equal to 0 here. So this is why this is the restricted model. And so here, the null hypothesis would be that these coefficients here, the parameters actually on the interaction terms would not be significantly different from 0. The alternative is that they are jointly significantly different from 0. So that's what we're testing. So we can estimate, first of all, the restricted model. This is the restricted model. And once we estimate the restricted model, we would be picking up the sum of squared residuals. And so we would call the sum of squared residuals underscore R to indicate the restricted model. If we estimate the unrestricted model here, we would be picking up the sum of square residuals. And we know that we will be testing for 4 restrictions because we have 4 parameters here to test. Okay, so now calculating an F statistic. Let's scroll down. So we estimated the restricted model. We obtained the sum of square residuals, estimated the unrestricted model. We obtained the sum of squared residuals. So notice that in the unrestricted model, what we're testing is that this coefficient here, all the coefficients are significantly different from 0. Now you see that individual, this one is not significantly different from 0, but these are. So we just want to know, are all of them, all 4 of them, jointly significantly different from 0? And to do that, we are calculating the F statistic. So here we have the sum square residuals minus sum square residuals for the restricted model minus sum square residuals for the unrestricted divided by the Q restrictions, and this is the sum of square residuals for the unrestricted model divided by the degrees of freedom. We can display the T statistic, the T critical value, and the p-value for the test as we have done before. So this is the value of the F statistic. The critical value is here, so we see that actually the F statistic is higher than the critical value, and the p-value is also very small, less than 0.05. Therefore, we are concluding that the coefficients are jointly significant. All of this could be done much quicker now by using the f-test, using the Stata commands. So here we have that we're running this model, and then we're testing whether the coefficient of female and all the interaction terms is equal to 0, and we obtain the same test statistic for the F statistic and the p-value, and we're concluding that actually these coefficients are jointly significantly different from each other. Now, what this means is that because we have significant differences, we should be estimating the full model here as opposed to the restricted model, or we should be estimating 2 separate models for males and females, because again, all of these coefficients are jointly significantly different from 0. Now, if we want to do the Chow test for differences across groups, that basically gives you exactly the same results as the f-test. The only difference here is that instead of estimating an unrestricted model, what we're going to be doing is we're going to estimate 2 different models, one for female and one for male. So here we would have an unrestricted model for females, which would be regression of wage on the independent variables if female equals 1. And here regression of wage on all the independent variable if female equals 0. So this is for the males. So we would run these separate models, the unrestricted ones, and get the sum of square residuals from them. And then we have the restricted model of wage on education, experience, and tenure. We would get these 3 independent variables, the number of observations, and the sum of square residuals here. Now, the way we would be calculating the Chow F statistic, everything else is the same as the F statistic before, except that here, instead of doing the sum of squared residuals for the unrestricted model, we would be summing up these 2 sum of squared residuals, one for each of the groups, for females and males, for females and males. And these are just a little bit differently defined degrees of freedom, but we would see that the result here would be actually exactly the same F statistic, F critical value, and p-value as in the previous test. So here is the Chow test for differences across group. This is the restricted model where we have the same intercept and slope for males and females. These are the results that we get in terms of the coefficients. So now if we estimate 2 different the two different non-restricted models, we have, this is the model for females, this is the model for males. And so we do see that this coefficient, we would be comparing this coefficient to this one, and then this one coefficient to this one, and this coefficient to this one, and this coefficient to this one. So we want to see if these coefficients are jointly significantly different from each other. This is what the Chow test is doing. Okay, so if we calculate, as I said, the F statistic, the F critical value, and the p-value for this F test, we would see that these are exactly the same results as before. And because the p-value is less than 0.05, we would be concluding that all the coefficients are jointly significantly different from 0. And what this means that we should be estimating different models for males and females instead of one model for both groups. And again, this Chow test is an equivalent way to the F test of how to test for significant differences. So thank you for watching.